talked about the common source circuits. We've talked about the voltage gain, the input and output resistances, and certain advantages in which this configuration is beneficial. Now, in this video, I'll try to explain you the common drain configuration. It's also known as the source follower amplifier. Now, there are certain advantages to this configuration as well. For example, you will find out that the output resistance in this configuration is small. That it's primarily dominated by the transconductance gain. And due to the small output resistance, the loading effect is minimal. So this configuration can derive the electronics which is connected at the source over here. For example, this is a NMOS source follower or common drain amplifier. Okay, because of the low output resistance, the loading effect when this circuit is integrated with further circuit is minimal. Okay. We'll also see that the voltage gain in this configuration is positive. So as opposed to what we had in a common source configuration, there was a phase inversion between the input and output. The phase was on 180 degree out. It was 180 degree out of phase. The input and output was not in phase. So here, although the voltage gain is a little less than unity, but it turns out that the input and the output is in phase. So it's also called the source follower for the same reason, because the output you'll see at the source is going to follow the input. Okay, with a very small small gain, positive gain. So the second type of MOSFET amplifier to be considered is the common drain circuit. Okay, so this is a common drain circuit. Why it's common drain? You can see that in this configuration, if you're going to construct the AC circuit, then this DC biasing, the DC bias terminal drain is set at will be the common ground of the signal in the AC equivalent circuit. Similarly, you can forget about the impedance or the capacitive reactance of the coupling capacitor. So if you want to draw the AC equivalent circuit, you can see this: the drain terminal is going to come at the common signals, common point of all the signal. Okay, it will be a common ground. So okay, let's start with the VI, which is the input being applied at the gate. Okay, then we have the output source resistance, RSI. So it's like this. And then next is the biasing resistors at the gate of NMOS. And you see that for the AC equivalent circuit, VDD is set to 0. So R1 is the other terminal of the R1. One is at the gate and the other node is grounded. So we can have this configuration as such. This R1 is going to come in parallel with R2 because R2 has one node. They're sharing the same common node at the gate. This is the gate. Okay, and then this is the drain, which is grounded, signal ground, and then we have the source from where we are taking the output. Okay, so this node is common in both biasing resistances R1 and R2. So the other node is at the signal ground. Okay, so it's like this. You'll have a parallel combination of R1 and R2, which are going to introduce some loading at the input. Okay, depending on whatever is the value of the source resistance RSI, there will be some loading at the input. So what it means is that the entire input is not going to be present at the gate, right? So it will be a fraction of VI at the gate terminal. Okay, and okay, so this is my gate terminal in the AC equivalent circuit. And then if I start with the source, first of all, you see the direction of the current is outwards. Okay, it's out from the source. So I can draw the current source because I know that the amplifier is an NMOS common drain amplifier. It's a transconductance amplifier in nature. So that means it's a current source. It's a dependent current source. And this dependent current source has a value of, it's given by transconductance gain GM VGS. Okay, the input is my voltage, AC voltage at the gate source terminals, and the output is the current. Okay, so GM VGS is in amps. Okay, now if this is the source terminal, then you see this this is output from the source. Then there is a resistor RS which I see is connected over here, and this is also grounded. And this is also ground. So this is RS. So I have gate terminal, I have source terminal. One other thing is that between drain and source, I mean, there is a, if you recall, there is a small signal output resistance of an amplifier given by R0 if you have a finite channel modulation parameter lambda, then R0 is given by 1 by lambda I0 or ID current, which is the current from drain to source. So this is the circuit. So your drain is now connected. You're taking the output from the source, so this node is source. Okay, so let me draw this as V0. V0 is my output AC signal. Okay, and this node is grounded. So you see that drain is grounded. The drain node is grounded, and the output is being taken from the source node. Okay, this is an AC equivalent circuit. Okay, so an example of this circuit configuration is shown in figure 26. This is figure 26, and as can be seen in the figure, the output signal is being taken off from the source with respect to the ground, and the drain is connected directly to the VDD. Now, since VDD becomes the signal ground in the AC equivalent circuit, which you see over here, okay, the drain is becoming the ground. So we have the name common drain for this configuration. Okay, just like the common source where the source was grounded, now we have the drain which is grounded. Drain acts as a signal ground, as an AC signal ground. So the more common name is source follower. Okay, so for the reasons that I have mentioned earlier, you will see this when we take some examples, that the output will be following the input. So that's why it's also called the source follower. Okay. Now, okay, I have this configuration over here as well. So this is my VI. Then I have the output source resistance RSI, VIN, which includes at the node parallel combination of the biasing distances. This is my gate terminal. Then I have a dependent current source. So at source, I have this resistance RS. Okay, and then there is an output resistance small signal, another small signal parameter R0 due to the modulation parameter lambda, which is given as 1 over lambda IDQ. Okay, so we have derived this parameter in the past few lectures. You might want to have a look at that. This is 1 over lambda IDQ. This parameter is Q dependent, that is Q-SYNC dependent parameter, one of those parameters. Similarly, your transconductance parameter is also Q dependent, okay, where the transistor is biased. So, okay, now this is a AC equivalent circuit model of the transistor consisting of the small signal equivalent circuit of NMOS transistor in a source follower configuration. In figure B and figure A are equivalent circuits, but in figure B you'll see that, okay, if this is the gate terminal, then this VGS means that this is source, and you see the direction of the current is the same, so it's coming into this terminal. So if this is the source terminal, the direction is as such, and then you have created a common ground. So this is my drain. You can see this now. It makes more sense that this is a common drain CD configuration of NMOS device. Okay, so for example, R0 has one terminal at the drain, which is the ground. So R0 one terminal is at the, one node is at the is connected to the signal ground. The other node is connected with the source. So these are the source nodes. These are the source nodes. Okay. Similarly, at the source node you have the resistance RS. The other is at ground. So you can draw this. These are the equivalent configurations. One and the same configurations. Okay. So the small signal equivalent circuit, assuming the coupling capacitor acts as a short circuit, is shown in 27A. So we are not considering this coupling capacitor CC, it's short circuit. Okay. So the drain is at the signal ground. The drain, as you can see now, is at the signal ground. And the small signal resistance R0 of the transistor is in parallel with the dependent current source. So figure 427B, so this is 27B over here, 27B, is the same equivalent circuit, but with all the signal grounds at the common point, and that common point happens to be the drain. That's why this is known as the common drain configuration or the source follower configuration. Another thing to note from here is that you see VIN, which is available at, so for example, VIN, which is available at the gate terminal, the AC Vin, is is a fraction of the original input voltage source. Okay, so your biasing resistance is R1 and R2, which is the input resistance of the transistor as well. If I write it as such, so R1 parallel combination R2, it's in a voltage divider configuration. So I can write this as R1 R2 parallel, then again R1 R2 parallel combination plus RSI, which means that there is a loading. Okay, so you don't have the entire input signal Vi present at Vg at the gate terminal. It's a fraction of the input AC signal Vi. Okay, so depending on the value of the biasing resistances, usually the output source resistance is not that much large, but if R1 R2 is larger, is a large value, then your loading effect is minimal. Okay, so if R1 R2 biasing resistances, these biasing resistances over here, if R1 and R2, the parallel combination of R1 and R2 is a large value as compared to the output source resistance, then it results in a minimal loading effect at the input. So that means the maximum of the input is available as an input at the gate of the amplifier. Okay, so okay, now we are again in this analysis, the small signal circuit analysis, we are again neglecting the body effect. If you recall, in the body effects, we said that if the source, if this terminal, source terminal, is not at the ground terminal and it's not connected with the body, because the body of the MOSFET is at the ground, and if they don't share the same common ground, signal ground, then it turns out that uh, there's an AC source BS, which is bulk source uh, small AC signal that develops between the body and the source. And due to that, you have a back transconductance gain, GMB. And owing to this, you have another current source. You have to consider another current source in the small signal transistor model besides GMVGS. There has to be another current source, but we are not considering this back transconductance gain. So we are assuming we are neglecting the body effect mainly. Okay, so we are assuming the source again. This whatever is the potential at the source, we have the same potential of the body. So VBS is zero. VBS is zero. So we are neglecting the body effect. Now the output voltage, if you can, so I have the same circuit. This circuit is drawn over here. Okay, so I brought it over here. And you can see that the output voltage is, so if you consider this the current source, then this is GMVGS. That's the current which drives the parallel combination of RS and R naught. So it's GMVGS time RS R naught. That is my output voltage in volts. Okay, that's my AC output voltage. And if you write a KVL equation from the input to output, it results in the following relationship. Now, if you look the input and output relationship, this is my input and this is my output. Then applying the KVL, okay, this is my output node, I must say. Then you can see this, that Vn is equal to VGS, Vn is VGS plus V naught, okay. And what is V naught? Well, V naught is right here, okay, it's GM So I have the same situation over here. So Vn, apply the KVL over here, right? So Vn is equal to VGS, the voltage drop between the gate source terminal, and then the output, which is taken from the source. This is my source terminal, okay? So just remember that this is my source terminal, this is my drain terminal, and again, this is my gate terminal, okay? So whatever is the input voltage available at the gate terminal is, it can be bifurcated into two voltages, that is VGS and V naught, okay? So since V naught is also in terms of VGS, this is my V naught, okay? And you can express, you can take VGS common, and then you can express in terms of V in, which is on the left hand side of the equation. So VGS is 1 over 1 plus GM RS or not. Now if you wish to write this in a voltage divider configuration, you can take this Vn out, and again you can express this as such. You can divide the numerator and denominator by GM, the transconductance gain. Now if you remember, GM is the transconductance gain in amps per volts. Okay, I mean this by definition GM is given as twice Kn. If you recall, it was of the form VGS minus VDN for NMOS device. So the idea is that this this has the what it means is that your input is volts and the output is current. Okay, the output is always the current. So that's why these MOSFET configurations are also known as, these are also transconductance amplifiers. Okay, so for example, if the input is VGS, the output is the current. Okay, the output is GM-VGS. That's the current source. So you can see over here, if this is GM is amps per volt, then 1 over GM becomes volts per amps. So that is ohms. Okay, this is ohms. So you see you are adding ohms to ohms. So this is the voltage divider principle. And so you can see the above equation is written in the form of voltage divider equation, in which the gate to source resistance of the NMOS device looks like a resistance with a value of 1 over GM. What it says is that RS parallel combination of R naught is at the is at the source terminal. So if you're looking over here inside of the source, then you have another resistance 1 over GM, which happens to be the resistance of the source terminal. Okay, so you have another resistance 1 over GM, which is going to take some fraction of the Vn. Right, so it's not the whole VGS. VGS is some fraction of V in, okay, which is available at this node. So 1 over GM is the source resistance, you can say. So more accurately, the effective resistance looking into the source terminal, ignoring R naught, is 1 over GM. Okay. So the voltage Vn is related to the source input voltage Vi by, now if you, what we've written before is, if this is my input resistance of the amplifier, okay, so you neglect this part is my source part. Okay, this is my input AC source, and this is my output resistance of the AC source. So so this happens, this entire resistance is my Ri, and this is the Thevenin input resistance of the amplifier. Okay, so what is Vin in terms of Vi? You can express this as Vn is equal to Ri over Rsi plus Ri into Vi. Okay, so if you look at this figure over here, then your Vin is Ri in terms of voltage divider is Ri over Ri plus RSI into Vi. Okay. Now, if like I've said before, if you're for whatever is the input voltage, if RSI is small compared to Ri, then the loading at the input is minimal. Okay, that means the input voltage available for the amplifier is completely available. I mean, it's not being loaded. The input voltage at the amplifier is Vi. Okay, it's not a fraction of Vi, it's Vi. So it depends on whatever is the value of this biasing resistance. This biasing resistances are going to dictate the loading at the input. Okay, if R1 and R2 parallel combination is higher than RSI, then you don't need to consider any loading at the input of the amplifier. Okay, so Ri is which is the parallel combination of the biasing resistances R1 R2 is the input resistance to the amplifier. Okay, now the small signal voltage gain can be derived using the following equation, and it becomes, if you start from here, VGS was equal to Vn over 1 plus Gm Rs parallel R naught, and how we derive this was by considering the KVL relationship. You see Vn can be bifurcated into two voltage drops, that is VGS and V naught. Okay, so this is my VGS and then this is my V naught. Okay, Vn is providing me VGS V naught. V naught is the output voltage, so here is my output voltage. Okay, and this expression can also be written as such, right, as we have did before. Okay, so 1 over Gm is my resistance. So I have these two equations derived before. So using all these two equations and this above equation, I can come up with the voltage gain. So what you need to do is just substitute for VGS. Just bring this VGS over here. Okay, and for Vn, just substitute this Vn right over here. Then that means the output voltage V naught will be in terms of Vi, right? Vi is going to come from here. This is my Vi. So you will have this part over here, and this part is going to come over here, and you can take the Vi to the left hand side, and this becomes the voltage gain. So my output voltage V naught by Vi output voltage by input voltage. This is the input voltage, this is the output voltage. This is my voltage gain. Okay, and you can see this is coming with a positive sign, which means that there is no phase inversion between the input and output voltages. So if you're going to, you want to simplify this a little bit more, you can write this as such. You can take this GM inside, so it becomes 1. Okay, and then again you want to take the RS parallel combination R naught in the numerator, and then we'll just multiply this with GM. So you end up, if you do some algebra like this, you end up a relationship like this. Or alternatively, if you still want to write this RS R naught independently and want to write this in terms of 1 plus GM. 1 plus GM is my resistance. Again, this is ohms, okay, volts per amps. So these are equivalent expressions. Again, this is my voltage gain, okay. So which is again written in the form of the voltage divider equation, okay. This is voltage divider equation. This is also voltage divider equation. Both are voltage divider equations. And if you look closely, the other thing is that you see in both the cases, the denominator turns out to be greater than the numerator. Again, the denominator over here is greater than the numerator. So that means my voltage gain for the common drain configuration CD or source follower is always positive but less than unity. Okay, it's always positive but it is less than unity. So I can say my voltage gain of a common drain voltage is going to be between 0 and 1. Okay, it's always between 0 and 1. It's a positive quantity but less than unity. Okay. So closed expression of the above voltage gain equation shows that the magnitude of the voltage gain is always less than unity. Let's take one example. This is 4.7 from your course text. What it says is that calculate the small signal voltage gain of the source follower circuit in figure 26. Now this is figure 26. As you've seen before, this is a common drain configuration. Why? Because my drain is at signal ground, right? And this is my small signal equivalent circuit model, okay, AC circuit model with the transistor being replaced by small signal equivalent circuit model. This is the transistor, small signal parameters. Okay, RS is the resistor or the source. This is my source. This is the gate, and then the drain is common. Okay, it's a common ground. So assume the circuit parameters are VDD is given as 12 volts over here, and R1, R2 are given as 162 and 463 kilos over here, and the biasing resistances, we have these values, and RS is 0.75 kilos. Okay, this is the output source resistance. Okay, so now transistor parameters, the threshold voltage is given as 1.5 volts, the conduction parameter is 4 milliamps volt squares, and then you have this channel width modulation parameter, lambda is 0.01 volts inverse. So assume RSI is 4 case. Okay, so let's start with the DC analysis. But before that, you are also the DC analysis results are I mean in the example you're not required to do the DC analysis completely. So you are given the quiescent current IDQ, which is 7.97 milliamps, and VGSQ is 2.91 volts. So the small signal transconductance is therefore GM is twice Kn VGSQ. Just substitute those values. So you have what is the value of Kn? Kn is given as so Kn is 4 milliamps per volt square over here, right? And then you have the VGSQ. So you have the Q point. So you have VGS over here, VGSQ and IDQ values. You have VTN. VGSQ is given as 2.9 volts, so it comes over here, and then threshold voltage of transistor is 1.5. So transconductance can be evaluated at 11.3. Similarly, R naught is 1 over lambda IDQ. Just bring this IDQ value over here, and you have the output small signal resistance more or less 12.5 kilo ohms. Okay. Now the input amplifier input resistance Ri is in terms of the biasing distances R1 and R2. R1 and R2 because these are going to come parallel. So this is my Ri over here. And it's easy to calculate, just calculate the parallel combination of R1 and R2. So this gives you 120 kilos. Now you see that 120 kilos is a huge value as compared to the output source resistance. So that means the input loading is minimal. Okay, so the biasing distances are large. So VI is completely variable at, I mean, it's a large fraction of VI, 90%, 99% of VI is available at the gate. Okay, over here. Vin. Okay, so Vin is approximately, I can say, is equal to Vi, right? Okay, so this fraction is, you can say, is almost equal to 1. Why? Because this is equal to, this will be less than 1, of course, but a little less than 1. This will be equal to 120 over 124, right? So you can see this fraction is close to unity. Okay. So again, RS, parallel combination R naught. So 1 over GM is dominant over here because R naught is 12.5 kilo ohms. Okay, RS is 0.75 kilo ohms. So you see RS and R naught parallel combination is going to produce a resistance which is less than both of them. Okay, it could be 0.7 to a little less than 0.69, 0.68, something like that. But 1 over GM is going to dominate this voltage divider expression over here. But again, this expression is going to be less than unity. Okay. Also, this expression was also, I mean, if I said this is close to unity, but it's in fact it's less than 1. So the final result is less than unity. Okay. You can just substitute the values. Everything is nouns. You have found what is the transconductance gain. Okay. You have the DC analysis is already provided to you with the IDQ and VGSQ values are here, threshold voltage values are given, conduction parameters. So you have the transconductance gain with you, and you have the channel width modulation parameter lambda. IDQ is given, so you know what is R naught. So 1 over GM is actually it's dominating the gain over here, the voltage gain. Okay. So the voltage gain is less than unity due to 1 over GM addition, okay, which happens to be the source resistance. So you can see that the magnitude in this example of the small signal voltage gain is less than 1. Also, the voltage gain is positive, which means that the output signal voltage is in phase with the input signal voltage. So, which was not the case in common source configuration. Okay, you have a negative over here. Even with PMOS and MOS, the voltage gain was always negative. So, which means that there was a phase reversal between input output voltage signals in the common source configurations. So, since the output signal is essentially equal to the input signal, almost, the circuit is called the source follower circuit. Okay, so it means whatever is the input is being applied at the common drain configuration, the output signal is following your input. The output signal is almost VI. Okay, it's almost VI. It's like 86 or 90% of VI. Okay, so you can write this as about possibly equal to. In this example, this is 0.86 of VI. Okay, 86% of VI with the same sign. Okay. Although the voltage gain is slightly less than 1, the source follower is an extremely